Hello, beautiful viewers. You're welcome once again to another fascinating math video. In this video, we shall be considering problem from analysis, and in particular, we shall be applying the epsilon delta definition of limits to solving problem in limits. In fact, limits is a very important concept in calculus. When we say important, that is even an understatement. We can simply say that without limits, there will be no existence of the calculus. Before continuing the solution of this particular problem, I would like to add that I render an online math tutoring service. I also assist in providing solutions to assignments, tests, projects, and research work. I have a practical teaching experience which spans over a decade. I have tutored various levels from the primary level to the high school level and even to the undergraduate level. So if you're in need of any of these services, be very free to get across to me because I'm very experienced, competent, and prolific in this field of mathematics. I studied mathematics and I've been in it for quite a while now. So when it comes to ability, I have a special ability and skill in communicating mathematics in such a way that the respondent will get a clear concept of any particular discussion. So be very free to get across to me as you will gain great value from the online math section. Also, I would like you to like, share, comment, and also follow the page for more fascinating math video. In the group, I may not provide the detailed explanation on concepts. In fact, I will not really do great work in the sense that I will not do lengthy videos. But when you follow the page, over there in the page, you see a lot of interesting stuffs, mathematical stuffs. So be very free to follow my page to get notified whenever I post any fascinating math content. All right. We are looking at a problem from analysis and specifically a problem from limits. As I said, that limits is a standard structure of calculus. Without limits, there will be no calculus. What is calculus? Calculus can be simply put as elementary mathematics that is enhanced by the limit process. When elementary mathematics is enhanced by a limiting process, such elementary mathematics is called calculus. All right. Now let's look at this particular problem. You see, by using the epsilon delta definition of limit, show that the limits of f of x as x approaches 4 equals to, where f of x is equal to the square root of x. So how do we solve this particular problem? First of all, we shall give a general definition of the epsilon delta regarding to limits. Let's give a general definition for that. So proof. Now observe carefully that when we say the limits of f of x as x approaches C. C is equal to L. What do we mean by this? When we say the limit of f of x as x approaches C is L, what do we mean? You have to know the meaning of this symbol. Whenever it is written, what do we mean by this? This implies that for each, I did not say for all, but I mean for each. For each epsilon that is positive, there exists a corresponding delta that is positive, such that, all right, when you see me writing this, what I mean such that if 0 is less than x minus c, the modulus of x minus c, and that is less than delta, then we can guarantee that the modulus of f of x minus L is less than epsilon. This is the meaning of this particular symbol, that is this. So whenever you see me writing this, This statement is a limiting statement. The meaning of this is this over here. All right. So be very free to spend time with this particular definition so that you understand what it's talking about. Let me give a little explanation. Here it says that the limits of f of x as x approaches c equals L implies that for each epsilon that is positive, there will exist a corresponding delta that is positive, such that if the modulus of x and c is less than 0, and the modulus is if 0 is less than the modulus of x and c, and the modulus of x and c is less than delta. If that is the case, then all x satisfying this modulus inequality will imply that the modulus of f of s minus L is less than epsilon for each epsilon that is positive. So there is no restraint to epsilon. This can be any arbitrary positive number. All right. If there is always a delta that guarantees the modulus of f of s and L to be less, that is the modulus of f of s minus L to be less than epsilon. If there is such a delta for every epsilon that is positive, then we can say that the limits of f of x as x approaches c is L. All right. So the problem here is finding a delta that always guarantees that the modulus of f of x minus L is less than epsilon. If we can do that every time for any positive epsilon, then we say that the limit of f of x as x approaches c is L. Otherwise, we cannot say that. Otherwise, the limit does not exist. All right. So this is talking about distance. You know, when we say the modulus of x minus c, I mean this. Let me illustrate with this symbol. I mean this over here. When we say this, we mean that the distance between x, the points x and the point c, is greater than 0. And also that the same distance is less than delta. And all the points x that satisfies this inequality here should also guarantee this inequality for any positive epsilon. If that can be obtained every time, we say that the limits of f of x as x approaches c is equals to L. Otherwise, it does not exist. So it is very important to get a proper grasp of this definition. Time will fail me to really give a kind of provisional definition that will help you to see into this definition. However, I told you I offer an online math tutoring service. So if you're interested in such a service, we shall look at detailed discussion over there, and also follow the page because I'll be providing something like that also. All right. So let us look at how we can apply this definition, this general definition, to this particular problem. Over here, we are required to find the limits. We have to find the limits of f of x as x approaches 4. That is to prove that the limits of f of x as x approaches 4 is 2. And the function is defined by f of x equals to the square root of x. All right. So we want to find a proof that this is so, this statement. Now, what does that mean? It means we have to find a delta that will guarantee this expression over here in our definition, this expression. Note, in this case, our L is 2. In this particular example, I mean this, all right? Our L is 2 here, while our C here is 4 over here. So in the place of C, I'll be putting 4. In the place of L, I'll be putting 2, all right? So we have to show that there exists a delta that will guarantee this inequality. All right. So we can say that the limits of f of x as x approaches 4 equals to 2 means for each, I did not say for all, for each epsilon that is positive, there exists a corresponding delta that is also positive, such that if 0 is less than the modulus of x minus a less than delta, then the modulus of f of x minus, sorry, in this case I don't put a here. You know our c is 4 in this case, so I will remove this a and put 4 there. 4 less than delta, then the modulus of f of x minus 2, because our L is 2 now, alright, will be less than epsilon. So we show that such a delta exists. We shall show that such a delta exists. Alright, we shall show this. So now let's look at what we want to do. We want to establish a connection or a relationship between the modulus x of x minus 4 and the modulus of f of x minus 2. Alright, we want to establish a relationship between them. Now take note that we can write f of x. Now we have that the modulus of f of x minus 2 is equals to, now if you observe carefully, you see that f of x is given to be square root of x. Can you see that? Look at it over here. F of x is equals to what? Square root of x. So in this connection, we shall have, in its place, we shall have the square root of x minus 2. Alright? And this can be related to, we can relate, okay, let me show you something. Before that, look here. Let me wipe this off. Observe carefully that x minus 4, I mean this expression here, look at it. This expression here, can you see this expression? Can be written as this, the modulus of the square root of x all to the power 2 minus 2 squared. So that this is a difference of 2 squared, alright? Now this can be further written as the square root of x minus 2 multiplied by the square root of x plus 2. Can you see that? And from the modulus properties, we can write this last expression as the modulus of the square root of x minus 2 multiplied by the modulus of x, the square root of x plus 2. Alright? Now there's something you should notice. If f of x is to be defined, x should be bigger than or equal to 0. Alright? Now note that f of x is defined only for x bigger than or equals to 0. Alright? And if that is the case, these are conditions, as we have to be very careful with this condition. We have to be very careful with this condition, with the choice of delta. Let me explain on this a little so you get what I'm talking about. Let me explain on this a little. Now look here. If I say the modulus of x minus 4 is less than delta, this one have a special meaning. What is the meaning? This is meant by saying that x lies within delta units of 4. Alright? That is, if I have a number line, let's call 4 a point. Look at the point for 4. This is the point that corresponds to 4. Alright? Let me paint this, and this is 4. Then this symbol you see here means x lies within delta units of 4. That is to say, we take a scale of delta from 4 to the right of 4. That is, I mean this now. Let's say this is delta units. Alright? Also to the left, we take a scale of delta. So s lies within delta unit means s cannot, let me call this point A. Let me call this point B. It means s cannot take point A, neither point B. But a can take any point within points A and B. That is the meaning. Alright? Now for this to happen, since the function f of s is defined only for x bigger than or equal to 0, it follows that our delta must be less than or equals to 4. Why did I say so? Now, take notes. This point you see, point B has a number corresponding to it. How do we get a number? Is by adding this delta to this 4. When you add the delta to this 4, you get the number that corresponds to this point B. And the number here, in other words, the coordinates, the line coordinates of the point B. We have various kinds of coordinates. We have line coordinates, we have rectangular coordinates, and so on like that. All right. So when you add this delta to this 4, you get the coordinates of the point B. All right. Every point has coordinates, and the coordinates are numbers, and we can call them points also. So when you add delta to 4, you shall have the points, which is 4 plus delta. All right. Now, to get the coordinate corresponding to point A, we subtract delta from 4. And when that is done, we shall have the coordinates as 4 minus delta. All right. That is to say, x should lie within 4 minus delta, less than x, and less than 4 plus delta. Now, I made this condition that delta should be less than or equals to 4. Now, if delta is not less than or equals to 4, let's say delta is 5. If we put in the place of delta, we put 5, we shall be having minus 1 less than x less than 9. All right. Now, clearly, they are negative number. That means s can admit negative number. But the function is not defined for negative number. All right. So the only way to ensure that s is positive, bigger than or equals to 0, is to let delta to be less than or equals to 4. Can you see that over here? So that when we put 4 here, we shall have 0 is less than x, and that is less than 8. Can you see that? So when s take any number or any points within 0 and 8, we are sure that the function is defined. Otherwise, the function is not defined. So we must strictly remember that our delta, the choice for our delta, must be less than or equals to 4. Otherwise, the function will not be defined. And if the function is not defined, there is no need of speaking of limits, because limit is a study of the behavior of the function as a value of x approaching a certain constant value. All right. We observe the behavior of the function values as the variable x approaches a certain fixed value. So if there is no values of the function to observe because the function is not defined, the idea of limit will be destroyed. All right. So in order for us to solve this problem, our delta must be less than or equals to 4. So that's taken into account, we continue the problem. Let me erase this from here now for clarity's sake. So this condition has to be strictly adhered to. Very, very important. So I can add to this my statement, this my notes. Now I said note that f of x is defined only for x that are non-negative. Now to ensure this, delta must be less than or equals to 4. I've said that already. All right. So this should be remembered. Don't forget this. This is a very important condition. Very, very important. Now note, we said that x minus 4 is now equal to the modulus, that is the modulus of x minus 4 is now equal to the modulus of the square root of x minus 2 multiplied by the modulus of the square root of x plus 2. All right. Can you see that? Now observe carefully that this expression, let me call this star for example. This expression you see here, that is the modulus of the square root of x plus 2, is bigger than or equals to 2. Why? Because x can take a 0 value. And if x take a 0 value, look at the condition, don't forget this condition. All right. If x take a 0 value, we shall have the square root of 0 to be 0. And the modulus of 2 is simply 2. Hence the equality in the weak inequality, greater than or equals to 2. All right. Then s can take other positive values that will make the modulus to be bigger than 2. Hence we said it is greater than or equal to. And this 2 itself is bigger than 1. So by the transitivity property of inequality, it implies that 1 is less than the modulus of the square root of x plus 2. All right, you see that. Then on multiplying both sides of this latter inequality by the modulus of square root of x minus 2, we have the following. So multiply this one by the modulus of square root of x minus 2, we shall have the modulus of x minus 2 less than the modulus of square root of x minus 2 multiplied by the modulus of square root of x plus 2. Can you see that? All right, and this is equals to writing. This is equals to writing. When you work on this, don't forget with this became from star. From star, we can write this as x minus 4. That is, we now see that the square root of x minus 2, which can be written as f of x, because f of x is equal to the square root of x. Hope you remember that. Minus 2. We have seen that it is less than x minus 2. So this last line suggests to us that we set our delta to the epsilon. That is, for every epsilon, if this expression can be less than the epsilon, we will always guarantee this. But don't forget that epsilon is an arbitrary positive number. And being arbitrary, it can accept numbers such as 8. And if our delta accept, that is, if delta is 8, the function will not be defined. Do you remember? I have explained it before in passing. That our delta must, look at it here, look at the condition here. Look at it. The delta must be less than or equals to 4. But we are tempted here to set our delta to the epsilon because we know that for this, if we take this expression s minus 4 to be less than epsilon, then we are very sure that this expression will be less than epsilon, because this expression itself is less than this expression. So if this expression can be made to be less than epsilon, then we are sure to have this. But there's a problem. The choice of delta here is restricted. It must be as stated here. Look at it here. That is, delta should be less than or equal to 4. So because of that reason, we cannot quickly jump into a conclusion that delta should be epsilon, because epsilon is an arbitrary positive number and it must be arbitrary from the definition of our limits. All right, let's look at the definition once again. Don't forget the definition. Look at the definition over here. We see for each epsilon bigger than 0, the word each is an example of a universal quantifier. And because it is a universal quantifier, it takes into account every positive real number, all right, including larger positive real number and smaller positive real number. Though the concept of limits is actually strictly restricted to small arbitrary numbers, positive numbers. But this definition give us the liberty to extend it to any positive number. All right. So if when I will be discussing the provisional definition of this limit, from whence we get this rigorous definition, you understand from that point of view. All right. Because when we say a function approaches a limit L as S approaches a number C, means that we can make f of s as close to L as we please by requiring that x is sufficiently close to C. That is the provisional definition. What is the meaning of sufficiently close to C? And how close to C should S be? All these are not precise. So to bring about precision, we have to come by the epsilon delta definition. All right. So I'll explain that in greater details later. And I said you can also message me for an online math tutoring service, because I render such service, so that you can get a real-time discussion whereby you can ask me questions about points you are not clear of, and I will try my best to bring about clarity. I promise I will do that for you. All right. So let's go back to the problem. So take note of that our epsilon must be arbitrary, and if it is arbitrary, setting delta to the epsilon is therefore dangerous, because there's already a restriction to delta. We cannot take epsilon. So what do we in this case? We shall choose delta in such a way that both conditions are satisfied. What are the conditions? The first condition is that delta should be less or equals to 4. That is this condition here. That is the first condition. Then the second condition is that our epsilon is an arbitrary positive real number. So how do we guarantee these two conditions simultaneously? We choose the delta in a way that we incorporate these two ideas. Look at how we're going to do it. We can say, now let delta, okay, let me write first. I will since epsilon, so I will remove this from here. This is not accepted because it's arbitrarily positive. All right. So I can say since epsilon is an arbitrary positive real number. Can you see that? Real number, delta equal to epsilon is not a choice, as delta must be less than or equals to 4. Can you see that? What I'm trying to say. All right. So what will be our delta? So the delta that will guarantee both conditions will be, let me put it right, because when proving things like this, you have to make comments, mathematical comments, such that anybody reading through will get a proper grasp of what you're talking about. It's not just to write symbolisms, but you have to make the symbolism to make sense to whoever is going through it. All right. Now we can say if delta, or we can write first of all, we choose the delta in such a way, we choose delta in such a way that delta is less or equals to 4 and epsilon is arbitrary. The question now is, how do we choose the delta? Now look at it. If we say let delta be equal to the minimum of epsilon and 4, I think that we do. That will be all right. All right. Now epsilon can be above 4 and epsilon can be below 4. You know, it's a variable. It's an arbitrary positive real number. So it can be arbitrarily small and also it can be arbitrarily large. Now when epsilon is arbitrarily large, such that it is larger than 4, then the delta will be 4, because we said delta should be the minimum of epsilon and 4. So if delta epsilon is arbitrarily large, such that it is greater than 4, then our delta will be 4, and that is accepted because we said over here that our delta, look at it here, that our delta should be less than or equals to 4. So even though epsilon is going above 4, our delta will take the minimum value of epsilon and delta, and that is 4. All right. Then when epsilon comes below 4, that is arbitrarily small, positively small, then the delta will be the minimum of 4 and epsilon, and in this case it is epsilon. All right, the delta will be epsilon because it is not less than 4, because this condition shows that delta should be less or equals to 4. So you see that this choice of delta guarantee both conditions. So we can now come here and say, we can say now that therefore, let me write this, therefore if 0 is less than the modulus of x minus 4, and that is less than the minimum of epsilon and 4, then we are sure to have this f of x minus 2 is less than epsilon. We are sure. Can't you see that? Now look, let me illustrate something to you. If our epsilon is below 4, that is arbitrarily positively small, this inequality will be very correct. All right, will be very, very correct as f of s is defined. But if epsilon is bigger than 4, our delta will be 4. All right, our delta will be 4. Also, this inequality will also hold, and it will guarantee this condition over here. Now, because for every epsilon that is positive, there exists a delta. In this case, the delta is the minimum of epsilon and 4. There exists a delta that guarantees that the modulus of f of s minus 2 is less than epsilon for every or each positive epsilon. Because that always happens, no matter how small the epsilon, there must be a delta that will guarantee it. it shows that the function f of s have a well behave is well behaved. That is, they have a good behavior, a kind of constant behavior. That is, when it's approaching the value 2, the distance between 2 and f of s is getting smaller and smaller, and that is a very constant behavior. It's a predictable behavior. Because of that, the function is not erratic, and therefore the limit indeed approaches 2. So because of this, we have established, we can quickly say that the limits, therefore the limits of f of x as x approaches 4 is indeed 2, and this concludes the proof of this problem. So you take your time to go through the proof, go over it once, twice, and thrice for a proper grasp of this. Usually the epsilon delta definition is not easily grappled by students, but with time, when you frequently go through it, you will discover that it's so. All right, but at the first stage, when you read through it, you may find it difficult to grapple with it. But when you keep on looking at it, you watch the video once, watch it twice, thrice, if possible the fourth time, you will get a proper grasp of it. So thank you very much for paying attention. You do enjoy yourself. Remember, I render an online math tutoring service. I also assist in providing solutions to assignment and tests, projects, and research work. So if you're in need of any of these services, be very free to get across to me. Message me directly, as I said earlier on, so we can have a proper discussion of how your class should be organized. All right. Also, do me the favor, if you draw any value from this video, do me the favor to like, share, comment, and also follow the page for more exclusive fascinating mathematical content. Thank you very much. I love you all.